Okay, so it is my great pleasure to host Professor Kai Müller from Technical University in Munich here at UC Davis. Um, Kai Müller has done his PhD studies at the Technical University in Munich, Walter Schottky Institute, and has then gone to Stanford for a postdoctoral position. I was lucky enough to be one of the students working under him. And then he started a group back in 2019, I believe, at TU Munich, Walter Schottky Institute, and got an early tenure in 2022. His talk today, Dynamics of Non-Classical Light Generation from Quantum Dots, is part of our lecture in EEC 289L. So thank you so much for being with us, and take it away.
Thank you so much for the kind introduction, Marina, and the invitation to speak in your QuIST seminar. It's a great pleasure. This is also somewhat like a tutorial-ish talk, so if you have urgent questions on the way, just interrupt me. Otherwise, if there are questions where I think they are best to be discussed at the end, of course, there will be time for questions at the end. So I'm with the Technical University of Munich, however, on the Garching campus, which is 20 kilometers north of downtown, close to a small town called Garching, which you can see here in the back. This is an aerial picture of the campus from a few years ago, and my group is entangled over different locations on this campus. So on the one hand side, that's the Department of Electrical Engineering. It's also the Center for Quantum Engineering that recently was finished, so we're about to move in there. And still the Walter Schottky Institute, where most of our labs are until we can move them. So it's really spread across that campus. I really like photons for quantum. Why? Because if you look at different applications of quantum technologies, such as quantum communication, quantum computing, quantum simulation, or quantum sensing, it is actually interesting that the photons as a platform can be used for all of them. So quantum communication in terms of quantum cryptography or linking quantum nodes, quantum computing. You can do measurement-based quantum computing based on a highly entangled photonic graph state. Quantum simulation you can do with photons, for example, boson sampling or quantum sensing. So photons in that sense are my system of choice. And if you break all of these applications down into the perspective, what do you need to make them work? It comes down to 4 essential building blocks. You need to generate quantum light. You need to interface this quantum light. For example, spin photon interfaces that allow you to effectively implement photon-photon interactions. We want quantum memories to store the quantum information for extended periods. And at the end of the day, we want single photon detectors to extract classical information out of this quantum system after a measurement. So my group focuses on the engineering of all of these for building blocks and their integration into photonic circuits. And for quantum light sources, we mainly work with semiconductor quantum dots. For spin photon interfaces, mainly group 4 color centers and diamonds. Quantum memories, mostly rarest ions, and single photon detectors, mostly superconducting nanowire single photon detectors. And once we manage to get these things on the way and also chip integrated, we hope that we will be able to realize demonstrator experiments that then serve for our colleagues in electrical engineering as test beds. To span this breadth of research, my group operates a number of state-of-the-art quantum optics laboratories with a huge number of closed-cycle cryostats, including vector magnets, millikelvin systems, lasers, and a lot of toys. In my talk today, I want to address one very simple thing. I want to address the generation of single photons from a two-level system. So assume you have a two-level system here with a ground state 0 and the excited state 1. The system is in the excited state. Then the system will relax to the ground state and emit a single photon. Or if you like theory more, then it's just sigma A dagger. So lowering the system from the excited to the ground state and emitting out the photon. And it turns out that this is a fun, interesting side project where really understanding the dynamics have now kept me busy for more than 10 years. In particular, if you take into account that the system somehow needs to be brought into the excited state first, which affects strongly the dynamics of the emission. My experimental system of choice to test these predictions that we do are semiconductor quantum dots, in our case, indium arsenide quantum dots in the gallium arsenide matrix. So these quantum dots here are a few nanometer in height and a few 10 nanometer in diameter. So they're essentially pancakes. And this results then in confinement for electrons and holes because of the band gap difference between indium arsenide and gallium arsenide. They have very strong optical interband transitions. Since it's standard 3-5 semiconductors, they can be easily integrated into optoelectronic devices. And over the past 2 decades, the quality of these quantum dots has been significantly improved, such that now when we resonantly excite these excitonic transitions, so assuming this is roughly a 2-level system, and we scan a laser over such a 2-level system, we get nearly transform limited line widths due to the improvement in the optical quality. So how defect-free these quantum dots can be generated using molecular beam epitaxy. Now, from an application point of view, when we want to engineer the best possible single photon source, we need to fulfill a number of criteria. First of all, the single photon source should be pure. So in other words, we want the single photon source to emit 1 photon at a time and not more. To quantify the purity of the emission, we use a Hanbury, Brown, and Twist type of experiment. So the signal is split into 2 parts, and with 2 single photon detectors, we measure the cross correlation. So this is hopefully learned somewhere already a benchmark for the single photon purity. If you look at the cross correlation between these 2 detectors at time 0. So this cross correlation value here, G20, the measured degree of second order coherence, this is what we use to approximate the purity of such a source. In addition, for many protocols, we like to have indistinguishable single photons. So that means that the single photons that our source emits are identical from the complete wave packet form. This is important for two-photon interference, the so-called Hong-Mandel effect, where 2 photons that arrive at the beam splitter at the same time bunch and leave the beam splitter in a superposition of both photons going out one exit port and both photons going out the other exit port. So there's quantum state 2-0 plus 0D, and you will never have 1 photon going through each of these output ports at the same time. So they stick together both in one output and/or in the other output. And so indistinguishability is a parameter that we look at, and brightness and rate. So rate meaning how fast can I operate my source in a pulsed way? What's the clock rate of the experiment? I want that fast because the source that emits 1 photon per week is not exactly useful. And the brightness tells you how many of the photons that are emitted can you actually collect. And both of these aspects can be significantly improved by embedding the quantum dot into nanophotonic resonators that enhance the light-matter interaction. So they speed up the emission process using Purcell enhancement, and they redirect the emission to the detection channel where you can record them. And these are 2, I would say, now almost historic examples of a micropillar resonator and distributive and bullseye resonator, which are just different ways to implement this. Now, about 10 years ago, for semiconductor quantum dots, it started that papers were published about really well-performing sources that most of the time combined electrical contacts and different types of nanoresonators. The electrical contacts are useful because if you apply a little bit of an electric field, shallow defects are emptied, so you stabilize the electronic environment, and at the same time, the Purcell enhancement helps with increasing the indistinguishability because you increase the homogeneous line widths. So for example, a prominent type would be electrically contacted quantum dots in a micropillar resonator, quantum dots in distributive Bragg reflector circular structures, so bullseye resonators, or since a few years also electrically contacted quantum dots in open tunable Fabry-Perot resonators, where recently, even from Shanwei Pan's group, a system efficiency of more than 70% has been demonstrated. All right, a few years ago, it was probably the time when Marina and I were both in Stanford. I stumbled across that question that many of these papers say, okay, my indistinguishability is this, my brightness is that, and these are good numbers. But what actually are good numbers? Because the good number is if it would be perfect, and how close can you get to perfect? What is limiting you from not achieving perfect performance? And also, how does the excitation method impact your source performance? These were the questions that started bugging me then and have kept me busy now for a long time. So going back to the simplification, this talk is actually about how does the way how I get from 0 to 1 impact on the performance parameters of the source. And here I want to introduce a number of different techniques that you can use that we've developed over the years and talk about their performance metrics and their advantages and individual disadvantages. So the first one is going to be a resonant excitation. The second one is going to be a two-photon excitation of a two-pass cascaded quantum ladder system. The third one is going to be stimulated generation. The fourth one is the so-called swing-up excitation, and that will be compared to a technique that I pioneered more than 10 years ago, which is phonon-assisted excitation. Great. I'm an experimentalist, but to do these fundamental things, you need theory as well. And I was lucky over the years to collaborate with a large number of different theorists from whom I learned quite a lot. So in addition to measuring the source parameters, we also simulate what's going on. And there we're mainly interested in G20, so the purity, which is from the Henbury-Brown QuIST type experiment, or the indistinguishability from the two-photon interference in a Hong-Mandel experiment. There are now many different techniques how you can calculate that. One that I use to illustrate here, because it's conceptually simple, but mathematically or computationally inefficient. But we set up the Hamiltonian, so we set up where are our levels, where are our driving lasers. Then what we want to calculate are correlators of the specific form here. And this can be done with a quantum-optical master equation using an extended form of the quantum regression theorem. So what I'm trying to say here is with a bit of mass and a lot of computational power, we can then also simulate what we can play in the lab with our quantum dot and the laser. The sample structure that we use for these fundamental experiments looks like this. We have our layer of quantum dots embedded in the intrinsic region of a diode structure. And this is then on top of a distributive Bragg reflector to form a very weak cavity. So this cavity is really not efficient in terms of photon extraction. We get about 1% of the photons that the quantum dots emit. However, it's a very broad band cavity, so it does not affect the spectral response of the quantum dot. And when I do these very fundamental schemes where I want to compare different excitation techniques, it's quite useful if the cavity is not making my life more complicated. Great. So the quantum dots are in the intrinsic region of this diode structure in a specific distance between the Fermi reservoir. And this allows us to deterministically charge and uncharge the quantum dot. So if I lower my electron level here to below the Fermi reservoir, an electron will tunnel in from the back contact into my quantum dot. Then the ground state is a single electron spin, and the excited state is a so-called trion consisting of 2 electrons and 1 hole. Important take-home message is that the charged exciton transition in such a quantum dot is a prototypical 2-level system. I can also lift the energy level of the electron above the Fermi reservoir. Then the electron tunnels out and I have an uncharged quantum dot. And the uncharged quantum dot is something that we'll come to a little bit later. It's a 4-level system, a so-called two-pass cascade, which I can exploit for some of the other protocols. Great. Let's go to the first protocol. We resonantly excite a two-level system. So now I ask, what is the chance for the system to be in the excited state as a function of the pulse that flies in and is absorbed? What we want to have is that the pulse drives the system up from the ground state to the excited state. Then it's perfectly prepared in the excited state. And subsequently, the thing emits spontaneously a single photon, and we're good. Unfortunately, it can also happen that while the system is being driven, so during the presence of the laser pulse, the system can relax to the ground state, leaving some energy left in the excitation pulse to drive the system up again. So in this case, while the laser is there, the system emits the first photon. And since the laser is still there, it can be re-excited and submit a second photon. So even though it's just a two-level system, there is a chance that for one laser pulse, we get two photon emissions. Now, this obviously depends on the pulse length, because if the pulse is much longer than the spontaneous lifetime, this thing will emit many, many photons during the presence of the pulse. And the shorter I make my laser pulse, the higher is the purity of the emission. And this is something that we can simulate and do an experiment and see it matches very well. So indeed, resonant excitation is nice, but it has limited purity because of this reexcitation effect. Now that we understand reexcitation, let's try to get rid of it. So therefore, we now switch from the two-level system to the four-level system. The four-level system has a ground state that's an empty quantum dot. It has an excited state, which is the so-called biexciton, consisting of 2 electrons and 2 holes, and it has 2 intermediate exciton states. These 2 intermediate exciton states are there because electrons and holes have different spin configurations. So you can think about electrons spin up, holes spin down, or the other thing. Then they couple, and because the quantum dot is not perfectly rotational symmetric, we have 2 different polarized ways to get from the ground state to this uppermost excited biexciton state. One couples to vertical polarization, and the other couples to horizontally polarized polarization. And very importantly, the transition from the exciton to the biexciton here is detuned from twice the exciton energy due to the so-called binding energy. So the Coulomb interaction is the result. Here I have just one exciton. If I put another exciton in there, 2 electrons, 2 holes, they will interact and change the energy. And this allows us now to drive the system from the ground state to the excited state using an effective two-photon excitation. So I tune my laser energetically in between these, and then the laser will be detuned from the exciton and from the exciton to biexciton transition. Or in other words, I put my laser here. You cannot see it because I additionally suppress the laser with polarization. But after I excite the system to the excited state here, I get 2 photons emitted, one here at the red frequency, one here at the blue frequency. And now our idea is that if we drive the system from the ground state here all the way to the biexciton state, the re-excitation should be suppressed, because in order to be re-excited, the system has to decay first to the intermediate state and then to the ground state. So in contrast to the resonant excitation, where the system just needs to emit 1 photon before it can get re-excited, in this scenario, the system has to subsequently emit 2 photons before the system can be excited again. So therefore, we expect a significantly higher single photon purity. And indeed, when we do this experiment, we can see that the center peak here, G20, is almost entirely suppressed. And now taking this data here from the 2-photon excitation of the biexciton in red and comparing it to the two-level system that I had on the slide before, we can observe the same thing in simulations, that now instead of a linear dependence of G20 on the pulse length, we now have a quadratic dependence of G20 on the pulse length. So in other words, for very short pulses, the single photon purity is significantly higher, and we can build a source that has a 2-photon error rate in the order of 10 to the minus 5. So only every 10 to the 5th time you would get occasionally 2-photon. Otherwise, you just get the 1-photon state that you like. You can see here that the error bars are really large. This comes from the fact that the detectors used here in this experiment a few years ago were avalanche photodiodes. They have dark counts. You have to take the error of the dark counts into account, which gives you metrology-wise a nightmare. Meanwhile, we've repeated these experiments with superconducting nanowire single photon detectors to get better error bars. I see there's a question. Yes, please. You mean the emission processes? Yeah, these are technically it's interband transitions. So it's an electron from the conduction band to the ground state to the valence band in this quantum dot. Yeah, excellent question. So with quantum dots, it's interband transitions. Effectively, it's a two-level system, but excellent question. Thank you. Well, we're just having a break already. More questions so far? Burning ones? No, then I'll go on and we discuss later. Great. So two-photon excitation of the biexciton gives us very good purity. How about indistinguishability? And here it turns out actually the indistinguishability is very bad. This is something that for a theorist might have been clear from the beginning in the experimental community. It was a big surprise a few years ago. Why is the indistinguishability bad? Well, we bring the system from the ground state to the biexciton state. Then the biexciton state decays. This is what you can see here, the population in red. It decays, building up population in the intermediate exciton state that then decays. What that means is that the two photons that are emitted, they are not emitted independently, but they are entangled in time. The emission of one photon, the emission of the first photon affects the time when the second photon is emitted. For the mathematical interested people within you, if you have such a system, you have a density matrix, you would do a Schmidt decomposition. So you trace out one photon to just look at the other. And you can see, yes, you can mathematically show the indistinguishability is limited to the ratio of the emission rate of the biexciton divided by the sum of the two emission rates from the two levels. I can also experimentally motivate why the indistinguishability is bad. Well, let's talk first about the exciton photon. So first, one photon is emitted, and after this photon has been emitted, a second photon is emitted. So there is a jitter in the time when the second photon is emitted. And if you send these two photons now to a beam splitter to overlap, if they jitter in time, if they arrive at different times, they cannot perfectly overlap. On the other hand, if you look at the biexciton photon here, the first photon that is emitted, here you can motivate the limited indistinguishability by the so-called final state broadening. Final state broadening means the final state of this transition is not a stable state. It is an unstable state that comes with a decay rate, and everything that comes with a time associated due to energy time uncertainty comes with an energetic uncertainty, which means the energy uncertainty of this first emitted photon here is worse. Great. However, we learn also that if we look at this ratio here, when we engineer the two emission rates, so the lifetime ratio, so how fast does this transition decay compared to how fast does the second transition decay, we can actually restore a high degree of two-photon interference visibility, so high indistinguishability, if the first transition here decays very fast and the second transition here decays very slow. And this is something that you can then, for example, engineer by using Purcell enhancement and Purcell suppression to make one transition faster and the other slower by putting it into a smart resonator. This is something that I would like to do, but on the way, we had more ideas what we could try. And one is to artificially decrease the lifetime of this transition here using stimulated emission. So now in this scheme, first, I drive the system from the ground state to the biexciton state using a two-photon absorption process. And then I send in a laser that is in resonance with this transition here to stimulate emission from that transition and effectively, at the time when I want it, quickly bring the system to the state here. So that therefore I kind of artificially enhanced the decay rate by making it instantaneously at the position in time when I want it. So let's look again at the decay curve of the system. Without my additional laser pulse, I would follow these dashed curves here for the biexciton and exciton that we had seen on the slide before. But now I can add my additional pulse and just swap the population of these two. And I can now decide when my laser pulse actually arrives. And now I can calculate several values as a function of this delay. So first of all, if the second pulse here arrives very late here on the right-hand side, nothing is happening because the pulse here would arrive when all the photons have already been emitted. However, if I send this laser pulse at a very short time and just now look at the intensity of this transition here, I can see that the number of photons that I get out is twice as high. And this is kind of nice because brightness is always good. It's also something that we can easily understand. If we put the system here, it can actually decay through these two different polarization paths that I mentioned in the beginning. But now, if I prepare the system and then immediately apply this stimulation pulse, all of the population will go to the horizontal channel and no population will decay through the vertical channel, which is why I can make this transition here then twice as bright. At the same time, when I look at the indistinguishability, if the laser pulse here, the stimulation pulse, arrives shortly after the first pulse, I can restore an indistinguishability of more than 99%. And if I look at the single photon purity, this is a little bit degraded at exactly time 0. So when these two laser pulses overlap, it's degraded. However, if I add a very, very small time delay, then it works really well that the single photon purity is still excellent, while I have at the same time an indistinguishability above 99%. Right, so much for theory. How does it look in the lab? Well, let's first look at the brightness. We cannot look at the depletion of this level because it obviously overlaps with a laser, but we can look at the brightness of this second decay here as a function of the delay. And indeed, the blue curve that we measured here resembles very well the blue curve predicted by theory. The next thing that we look at is the single photon purity. So now we do an experiment where we sit exactly here in this minimum, so a time delay of just a few picoseconds. And indeed, I still have a G to 0 in the range of 10 to the -4. So very good single photon purity. Last thing to show is indistinguishability. So we have this beautiful curve here. Now my students took the time to map out that entire curve. And you can see qualitatively it resembles the behavior very well. So the model seems to be valid. There is one small minority one small aspect that I really didn't like, and this is in simulations we can get the indistinguishabilities of 99%. In experiment we could only get something like 86%, so it's not as good as predicted by theory. However, for the quantum dot that we looked at here, also under resonant excitation, the indistinguishability was not as good. At the time, we were afraid that it might be the quality of our MBE that was causing the issue. Now, a few years later, we learned it was actually all just electric noise. So meanwhile, more people joined the building. Some people have some devices that radiate, that cause noise to be coupled into our quantum dot with a very sensitive electric field sensor due to the dipole moment of the quantum dot. So it was all noise, and the model here is correct. With this scheme, we indeed can generate single photons with a high brightness, with a very high purity, with a high indistinguishability, and in addition, we get to something for free, and that is the control of the polarization. Because if I set my stimulation laser to be horizontally polarized, my single photon will be horizontally polarized. If I set my stimulation laser to be vertically polarized, my single photon will be vertically polarized. And this is cool for some protocols where you need to modulate polarization, because then you don't need to modulate the polarization on your single photon, which is very sensitive to losses, but instead you just modulate the polarization of this laser here, and this polarization of the stimulation laser is then imprinted onto the single photon. Cool. Now, the next thing that we look at is the so-called swing-up excitation technique that was proposed by Thomas Bracht from Doris Reiter's group a few years ago. First experimental demonstration then from Yusuf Karli and in Innsbruck. We had then also looked at the system and investigated the coherence dynamics. So what is the swing-up excitation? Typically, if you have a two-level system, it emits at its frequency omega 0, so the energy that you have between ground state and an excited state. When we had done resonant excitation before, the laser here is tuned exactly into resonance with this two-level system. And what this thing does is, as I've shown you before, if the laser pulse is absorbed, the system is driven from the ground to the excited state. And on the Bloch sphere, that is like a boring rotation in the rotating frame. Now, the idea that Thomas Bracht and Doris Reiter had was, what about substituting this one resonant pulse by two pulses that are red detuned? So these two pulses have an individually controllable amplitude and frequency and width and so on. And if you find the right combination of parameters, you can actually see that the system is also driven from the ground state to the excited state, undergoing, however, quite some oscillations that look particularly funny if you follow the quantum trajectory on the Bloch sphere. So this combination of two red detuned pulses can also effectively drive the system from the ground state to the excited states. This is something that is interesting for applications, because here I could just put in my frequency filter in between in the detection channel. I let through the emission, I block the excitation, and then I don't need other complicated filter mechanisms to isolate the single photons. Now, when we do this coherent off-resonant excitation method, there's, as I mentioned, a huge parameter space, because we can detune both pulses individually and we can control their amplitude. We can also control their temporal widths and their delay. So it's a huge parameter space, which then for like this talk here, I can only give for few small examples. Right, so here in this simulation, we keep the lengths of both pulses fixed to 10 picoseconds. We make them arrive at the same time, and we fix the detuning of the first laser to minus 0.7 MeV, and we fix the power of the first laser to 8 pi, 8 pi meaning if it was a resonant pulse, it would be an 8 pi rotation. And then for the second pulse, we change the detuning, and we change the pulse area. And if we run the simulation, we can see that there are actually multiple resonances in this phase space here, where the brightest point here corresponds to a population inversion of 97%. So in simulations, it works really well. And these many lines here are the hallmark of this off-resonant driving to be a coherent process. Great. Now we do measure this thing in experiment, and we're very happy that our experiment resembles the theory quite well. So we also see multiple resonances, and they are in the phase space roughly where the simulation predicts. Great. Now, how well does this thing perform? What is the probability that we can invert the system? We run the simulation and the experiment here with the same parameters. And we see that in the swing-up excitation, this is the thing here in red, we actually get less photons than in resonant excitation. So this is a surprise, because both the Rabi oscillation and the swing-up should result in an inversion fidelity of 97%. However, we only get 67%, and there's also one effect already visible. The peak here is not only not as high as the resonant excitation, it is also broader. And this is an issue of all of these semiconductor environments. They are sensitive to high power excitation. If you hit your crystal too hard, you will have all sorts of lattice vibrations. You will generate free charge carriers. The carriers trap somewhere, they float around. So in order for this thing to work, you need a really, really clean crystal to get to very high performance. However, this is now the first demonstration of single indistinguishable photons from a swing up excitation technique, and compared to resonant excitation, there are like 15 or 20 years difference in development. So I'm optimistic that future sample generations can get higher inversion fidelities. We now compare the performance of swing up excitation with the performance of resonant excitation. In terms of single photon purity, quantified by G20, they behave more or less the same. And in terms of indistinguishability, we had 66% indistinguishability for this quantum dot in resonant excitation, 44% is indistinguishability using swing up excitation. So indeed, it is degraded, but that means, put it positive, there's way for improvement in the future years. Great. Final excitation technique that I would quickly like to mention as well is phonon-assisted excitation. This is something that now also goes back quite a long time that I had done these experiments. When you have the two-level system, you change the energy of your excitation laser, you scan it with a pulse area that corresponds to a complete population inversion. You can see here for the quantum dot a nice and clean peak. So when the laser is in resonance with the quantum dot, it is excited from the ground state to the excited state. Otherwise, I don't get photon signals out. Now I increase the power quite a bit, let's say 5 pi, 10 pi, 15 pi, so 15 times the pulse area that you would need for full inversion. At some point, you can see here this two-photon absorption resonance coming up. This is the one that I had used a few slides before to drive the system from the ground state to the biexciton state. But you can also see that red detuned from these transitions here, you get some broad absorption features. And they become even better visible when we now plot this thing here in a color plot. So from left to right, I change the pulse area. And the y-axis here is the emission energy. In resonance, I get clean Rabi oscillations for the exciton transition. Now at the position of the two-photon resonance, I get two-photon Rabi oscillations. But then blue detuned in the absorption spectrum, we get these additional absorption resonances. And these resonances result from the laser now having a higher energy than the two-level system. So it can actually emit an acoustic phonon and in the same process excite the two-level system to the excited state. Interestingly, it has been predicted from Doris Reiter's group that this complex interplay of a photon and a phonon should lead to an even better better purity than resonant excitations. In practice, we have obtained similar values for both of them. So just to mention this technique as well to complete the overview of methods. Good. This is what my group had done in terms of excitation techniques. I'd like to just quickly mention this is not the only thing that we do with quantum dots. We're also interested very much in fundamental and other applied things. So things that we've published recently. If you're interested in taking a picture, is investigating the origin of anti-bunching in resonance fluorescence, investigating pulsed Müller triplets or doubly dressed Müller triplets, three-photon excitations of two-level systems, correlations in the resonance fluorescence, investigating multi-photon scattering, and also engineering quantum dots that emit in the telecommunication O-band and C-band. Great. With that, I would like to thank the people from my group that actually did the work. So here highlighted are the people from my group working on the quantum dot project. So Lucas Hanschke, Eduardo Zubizarreta, Katarina Bros, Caroline Calcanio, Sang-Kyu Kim, and Friedrich Spresny, as well as many collaborators here also highlighted the ones that we have for this specific project. And of course, many thanks to the generous funding from various funding agencies that made this possible. So to quickly wrap up again, I hope I was able to convince you that resonant excitation is nice, but it results in limited single photon purity. Two-photon excitation allows you to avoid this bottleneck, so you get very pure single photons, however, at the expense of indistinguishability. The stimulated generation scheme allows for high indistinguishability, very high purity, high brightness, and control of the polarization. Swing up excitation is a very promising alternative, but it will need some more time to lead to the same performance due to the strong driving. And phonon assisted excitation is also an interesting technique. However, it also requires high power, and so far it has only demonstrated performance comparable to resonant excitation. And with that, I would like to thank you very much for your attention, and I'm looking forward to exciting questions.
Thank you very much, Kai, for an excellent talk. Questions?
I think I'm lost there. What was the difference between two-photon stimulated generation? Sorry, I'm sick. What was the difference between two-photon excitation and stimulated generation?
Right, yeah. So in the two-photon excitation, we just set a laser with the energy between the ground state to exciton and exciton to biexciton transition. So two photons are being absorbed, bringing the system from the ground state to this top excited state here. And from there, the system decays by emitting the two photons as spontaneous emission. So it's a really cascaded emission. In the stimulated generation, I forced the system to emit the first photon directly after the system was prepared in the ground state. So effectively, this thing here gives you two photons at two different frequencies that you can filter out, but that are not indistinguishable because they're entangled in time. Whereas here, I kind of drive the system with a small detour over this excited state exactly to the state that I want to have. So therefore, I prepare the system in the state at a very specific time, and I don't have excitation jitter of the photon, which then results in a very high indistinguishability. So it's I would say it's this is the thing that was before, and that was like a new development.
Yeah, thank you for the great talk. So in this phonon excitation scheme, this is making me sort of think of something like what people do with atoms, like motional cooling of atoms by driving the motional sidebands. I was wondering if this is something you could do with quantum dots to cool them, or if the phonon band is just like too much from both.
That's a very interesting question. So cooling the quantum dots in terms of their phonons, people see that if you actually reduce the temperature further and further, Michael Reimer from Waterloo had done an experiment where like they put a quantum dot into a dilution refrigerator to see that the line width gets even a little bit better if you go from a few Kelvin to 2 millikelvin. So it is the phonons are the remaining issue. However, it's also not entirely clear which phonons you're talking about, because the spectrum that I had shown, this is a kind of the bulk, well, it's the bulk spectrum of acoustic, it's bulk acoustic phonons coupling to quantum dots. So the spectrum itself, well, we can quickly go to this thing. This is also interesting. The sideband here, it's a combination of the density of states that increases like cubic, and then the coupling decays exponentially once the wave vector of the phonons gets very different in size from the quantum dots. So, but nevertheless, these are bulk phonons. Several theorists have in their simulations predicted that the quantum dot with this size should also have localized phonons, so really vibronic modes of the quantum dot itself. And now the question: can you use this coupling to further do sideband cooling? No experiment has been done yet. The coupling is quite strong, so it's not clear if it thermalizes too quickly. What has been done recently with quantum dots in actually with the nuclear spins of the quantum dots is to cool these using specific protocols and then excite single magnons in the nuclear spins. This is amazing recent work from Meta Atatürk's and Dorian Gangloff's group in Cambridge. Here with just the acoustic ones, it's an excellent question. I'm convinced that you can do something, but how far you can get might be limited due to this different, like really strong coupling to the phonons and unclearness what phonons you're actually talking to.
Thank you.
Thank you. Yes.
I have a question regarding the four-level state. When you showed us a graph for indistinguishability and for the graph, the well, you know what word I'm referring to.
Yeah.
It was lower. You were expecting 99%, but you had 80 something percent.
Yeah.
You said it was because of people entering the building.
Right. So this is the thing here. The theory had predicted 99%. We measured 86, but also in resonant excitation, you predict 99 and we measure 86. So this is could be traced to charge noise. So I will jump to another slide that I went over a bit too quick to illustrate how that works. And this is, we have now our quantum dot in this diode structure. So we can apply an electric field. And what I mentioned is that we can use this electric field to deterministically charge and uncharge the quantum dot by bringing in an electron. So and there's this X- regime where we work with a charged and the X0 regime where we work with an uncharged quantum dot. Now, if you go like here and zoom in, you can see that this black line is not flat. The black line is slightly tilted, and this is it's like slightly bending upwards. Unfortunately, I can't like really zoom here, or at least I don't know how it works. This is the so-called quantum confined Stark effect. The exciton in the quantum dot, it's an electron in the hole, has a static dipole moment. So if you apply an electric field, this dipole moment, the static one, couples to the external electric field. So by changing the electric field, I can change the energy of my two-level system. And now if the electromagnetic field fluctuates, so if the gate voltage fluctuates, also the energy of my two-level system will fluctuate. So if you look very fast, you would see this line in energy jumping back and forth. And if the energy changes, then the interference is also impacted. And this is why the indistinguishability is reduced.
Yes.
Thank you.
Outside.
Great job.
Thank
Thank you very much. So I'm wondering, when you do the measurement, is one quantum dot is under consideration, or you have a number of them?
Great. Yeah. So all experiments here were done for single quantum dots.
And your sample are the dots identical in dimension, shapes, and size?
Yeah, so now the question is, it goes a bit in the scaling. So the quantum dot consists of roughly 10,000 atoms. So no two quantum dots are the same. They vary in their lifetime a little bit. They vary in their energy. Depending on how you grow them, this spread in energy can be quite large or a little smaller. So Stransky-Krastanov growth typically leads to a full width half maximum of maybe 40 nanometer. Droplet epitaxy reduces it to 5, but it's incredibly challenging to get, by definition, identical quantum dots. The chance is highest if you take them from the same wafer. So like 10 years ago, Meta Atatürk has had an experiment where he entangled two spins using a scattering protocol, and they were like from the same wafer. But since it's 10,000 atoms, it's very challenging. And in order to make them as comparable as possible, you typically want to tune the energy using some mechanisms, so either a quantum confined Stark effect, or you also want to tune the strain to affect the symmetry. So if you just want to have two quantum dots that emit at the same frequency, that is kind of trivial. You search for two that are almost the same, and then you tune them into resonance using one of these tuning mechanisms. But if you want the two dots to be like even more comparable, then you need a lot of tuning mechanisms, which is also, in my view, quantum dots are great for photonic quantum technologies where one source generates you millions of photons or many entangled photons, but they are not my system of choice if I want to scale on the emitter side.
Yeah, of course, of course. So based on the top-down approach, can people do a better job with identical characteristics of the quantum dots?
I mean, top down building them, or
Fabrication rather than going there.
uh,
I know that's probably a
there are more tuning mechanisms that you can implement by engineering. So you can generate micro mechanical structures for in situ tuning. This is something that is very helpful. But other than that, to get them more homogeneous, there are different techniques being explored for a longer time. Also, for example, site selective growth, so that you think that's going in the direction of the things that you have in mind, that you don't let them grow randomly, but instead you pre-pattern the surface, so you make them take specific shapes and you make them grow on specific locations. There's a lot of potential in it, but it is non-trivial, and I think it will take quite some more time to produce good results. And in the past, it was always the problem that as soon as you grew on engineered surfaces, there were some defects involved, and whenever you have structural defects, you have charge traps, and that resulted then in worse line widths. But this is, in my view, this is a problem that can be solved, but it takes time and money. Thank you.
No questions? I have a question about, so you were showing how by kind of spontaneous emission, by using laser, you can make your biexciton go either horizontal or vertical route, and proposing that can be used for quick switching or polarization of single photons, which, to tie it back to our class, we did the BB84 experiments where you did manually, you were rotating Alice's polarization to generate that, and here what is proposed is just to use two different lasers. Now, these two transitions are not exactly the same energy. How different they are in the wavelength, and if you were to use this in a protocol, could you make it hard for Eve to separate these two polarizations just spectrally?
Yeah. So now the question is, I drew them here slightly different, and this comes from the asymmetry of the quantum dot. This splitting here is for Stransky-Krastanov dots of the order of 10 to 60-ish microelectron volts, for droplet epitaxy even less. And for these dots, it's typically 10 microelectron volts, so it's already quite tough for Eve to filter because the bandwidth of the photons is like a gigahertz, so that the bandwidth is much larger than the splitting. So separating them is not easy, but indeed this fine structure splitting here can be tuned using strain, for example, or electromagnetic fields. Was pioneered by Rinaldo Trotta, who's in Rome. And moreover, there are growth techniques for dots that have no fine structure. So also these quantum dots embedded in nanowires that the people in Canada grow a lot. They have no fine structure splitting. So yes, with the right dot, you make it already impossible for Eve. With these kind of dots, you will have to put them onto a piezo and strain for the two transitions to be tuned into resonance.
Thank you. And what happens if you shine both vertical and horizontal?
Great. Yeah. So this is another very interesting thing. Since this thing here is effectively a two-level system again, so you could see this exciton spin here as a qubit. You have a Poincaré sphere for the first transition that corresponds then to the Bloch sphere of your exciton, and again a Poincaré sphere for this other thing here. So it works with all polarizations, but it really depends. So if you use diagonal polarization, then your second photon will also be diagonally polarized. If you use circular polarization, if you send the stimulation pulse circular right-handed polarized, the second the emitted photon will then be left-handed circular polarized. So then they are opposite. There was a nice demonstration of this effect from Björn Jonas is the first author from Arthur Zrenner's group in Paderborn. I think it was the last work that got published before Arthur retired from 2022, I believe.
Any more questions? Yeah?
You mentioned a Poincaré sphere. What exactly is that?
Right. So you know the Bloch sphere for qubit. Before qubits actually existed or were conceptualized, you already had the concept of polarization of light. And the polarization of light has a sphere. It's identical to the Bloch sphere for a qubit, where you have with the two poles and then the superposition of these two giving you the full 3D sphere. You're welcome.
Questions? Feel free to also ask anything about career or doing research in Germany. Yeah, Liam.
This is kind of an unrelated question, but I remember when you were mentioning the method of photon excitation, you mentioned that the purity of the results didn't exactly live up to theoretical expectations. Could you elaborate a little bit more on why you think that might be and what you meant?
Yeah. So let's first let me first try to explain why it is expected to be better. When you do this phonon-assisted excitation, your laser is detuned from the two-level system. So you have basically a detuned driven two-level system. So in the now in the rotating frame of the laser, your two eigenstates are not identical, but are somewhat different in energy. And this difference in energy while you're driving, once this matches the phonon density, you get the relaxation from one to the other. And once the pulse switches, and these two eigenstates that you're looking at during the driving, they are a mixture of ground state, excited state, and so on. And it's only when the pulse switches off, the lower state is actually transformed into the excited state. So the lower state in the dressed states picture is then the excited state of the exciton or the two-level system once the laser switches off. So the idea behind is that only after the pulse is gone, your system actually is prepared into the state from where it emits. So consequently, reexcitation should be strongly suppressed. My belief is that most of these theoretical predictions were done for temporally square-shaped pulses. Because apparently if you have something of constant amplitude and just leave it run for some time, that's easy in the simulations. However, getting temporally square pulses in the lab is incredibly complicated because you would need a sync shaped frequency filter with the phase jumps in between. So here it's either something that is Gaussian or square-like. And I believe that this nice switching from a non-emitting state to an emitting state only when the pulse is gone, this is washed out in all experiments to date. So as a result, the re-excitation can occur.
Thanks, Kai, for a great talk.